So, good morning, students. In soil chemistry, we're discussing about the electrical double layer, and we will see what are the different theorems are there and what is their role in our in soils. Very first, students, we will discuss what is an electrical double layer. We will see some introduction part. Generally, we know that clay is a negatively charged particle, right? Of this negative charge may comes from isomorphous substitution, which is called constant charge or permanent charge. On there is another type of charge, temporary charge or pH dependent charge. Between these two charges, between these two phenomena, we will get this negative charge. So generally, has as it was so electronegativity charge, so your clay particles can attract the cations. So that's why the clay cations can be attracted by the clay particles because clay is itself is a negatively charged one. The same time, so generally what will happen? So there will be uniformity. So generally, is that if you think this is a clay, it is a negatively charged one. So as it was negatively charged one, definitely there will be some positively charged particles will be attracted. So there are so based on this small theory, so generally what will happen, we get the two layers. One is our negative layer, one is our positive layer. So this is called the electric double layer. So based on this concept, there are many concepts are there based on this electrical double layer. We will read many concepts, how these negative charges were distributed, how this negative charge is there, and how these positive charges were attracted. All these things we will discuss. So very first, students, so this is what I'm saying. So generally, the first layer is a fixed layer, what we call a negative layer, and another one is called one theorem. It is called as a fixed layer. Another theorem is called diffusive layer. So like that, we will see all those things. Technically we are speaking charge. Technically, charge is a point charge, student. So the charge, whatever the charge present on the particle, we consider as a charge. That negative charge is called as a localized point charge. So for our customary reason, we feel so for our convenience, so for our need of scientific study, we hope that that negative charge was uniformly distributed over the clay surface. At the same time, second layer, the so-called second layer, because the positive charge is a second layer. So this second layer is a second layer is a double layer. It is completely liquid layer, students. This layer is completely solid surface. That is our clay particle, but the second layer is completely a liquid layer, completely liquid layer. So generally these positive ions will contract with these Jones, all this will happen, how the distribution, etc., will be taken place, we will see all those. And so based on that concept, so based on those, so as I said, these are negatively charged, these positively charged particles will be attracted by towards this negative charge. So based on this concept, we will see many theorems. Very first one is called Helmholtz double layer theory, fixed layer theory, or something. Many words with it, but very early developed theory is called Helmholtz double layer theory. And second one is called Guy Chapman. Okay, okay, I got it. So the Guy Chapman Helmholtz double layer theory and a Guy Chapman double layer theory. The Guy Chapman double layer theory is somewhat same thing was happening, but this is also called a diffused double layer theory. Diffused uh, diffused double layer theory. 1 minute, students. I forgot to record the class. Yeah, now it's okay. So and another one is called Stern model theory. So Stern double layer theory. This is the double layer theory. So there are some demerits in this Guy Chapman double layer theory, but that to overcome that Stern double layer. Stern is nothing but it's a combination of these two. So in Stern double layer theory, we can say Helmholtz double layer theory, Guy Chapman double layer theory. And finally, we will see the triple layer theory. So triple layer theory, this theory is exclusively for the sesquio oxides. So all these things, all these Helmholtz double layer theory, Guy Chapman double layer theory, or diffuse double layer theory, or Stern double layer theory, explains mostly for the silicate clays. But in triple layer theory, this theory is completely explained how the distribution taking place in sesquio oxides, that's iron oxides, how the iron oxides, because I know you can see in that part, in that particular things we can say OH minus ions and H plus ions will be there. So we will discuss about what is the triple layer theory. Another one is called Zeta potential. What is Zeta potential? We will see that that is very important concept. We will see about the Zeta potential. Very first, students, Helmholtz double layer theory. I will explain very simply, students. I don't want to confuse you. See, it's Helmholtz double layer theory is also called fixed layer theory, students. It is nothing but, see, some negative charges will be present. Some negative charge will be present on the clay surface. Okay, this is how this negative charge was present. So what will happen? These negative charges will be counteracted by the positive charge. Like this. This is completely soil solution. This is a clay surface, this is a soil solution surface. So as the distance increases, as that is called chi. This symbol letter is called chi. This one. This x was represented by like this. Okay. As the distance increases, the potential, the electric potential will be the electric potential towards this attraction will be decreases. So as the distance increases, what will happen? The linear potential distance will be positive cations cannot be attracted to the negative anions. So the towards the attraction towards the clay will be decreases. This is very simple and very simple theorem will be explained by this thing. As the distance increases, and this will be so this will be can be calculated, or this can be mathematically. This theorem is explained by this equation that is called chi. This xi is nothing but potential. Solid potential 4 pi sigma xi by dt is nothing but dielectric constant. So dielectric constant of the soil solution. Now we will see now we will see 1 minute, students. Yeah, this is regarding Helmholtz theory. So this Helmholtz double layer theory is explained by this potential xi is equal to 4 pi sigma psi by d. This for formula, students. Please remember this formula, Helmholtz double layer theory. Especially students, nowadays exam is going to be very tough, so they may ask this formula also. Plus, be confident. So coming to the same thing, students. The same thing which I explained was completely yes. Okay. So Helmholtz double layer theory. Now so it is this is I explained. So see, this is charge density. Sigma is called charge density. Xi is the distance, surface distance. This is a parallel plane surface distance xi, and d is dielectric constant. So this psi is nothing but total potential. So total potential is equal to 4 pi sigma xi by dielectric constant. So Helmholtz double layer theory mathematically was explained with this equation. That is example. And also you will see about this psi clearly. But these are all Greek letters, so that you will pronounce like this only. Okay, students. This is regarding the Helmholtz double theory. I think there is nothing to remember in this Helmholtz double theory. It is also called the fixed double theory, because here the positive negative is completely fixed. There will be close attraction will be there. As the distance from the surface plane of the clay particle increases, the attraction towards that cations will be decreases. And this was mathematically expressed by like this. So total potential psi is nothing but total potential 4 pi sigma psi by d. It is called the dielectric constant. This is regarding the Helmholtz double layer theory. Coming to next one is called Goy-Chapman double layer theory. This is also called as diffusive double layer theory, students. This is also called as diffusive double layer theory. It is quite simple, students. Similar to our Helmholtz double layer theory, but what was the difference between is nothing but the second layer is then the counter ions was completely dispersed like a dispersed. But in Helmholtz double layer, not like that. Everything was fixed. But here is completely dispersed in the liquid layer as the gas molecules in the atmosphere. It's quite similar. How the gas molecules are present in the atmosphere are being has been how the gas molecules are present in the molecule. Same thing was happening in this here also. That's why second layer is completely diffused double layer. So this distribution, the distribution of cations in the liquid zone completely follows the Boltzmann equation, and mathematically this was expressed. So this is what, students, see, these are the similar to our Helmholtz double layer theory only. The negative charge will be prevalent. This is the total potential. Xi is total potential. So negative charge will be there, and this is a soil solution. This is a potential this is a potential distribution as related to distance. So similarly, but all the cations, all the positively charged particles will be diffused, just like how the gas molecules will be present in the atmosphere is completely diffused. Similarly, as the distance increases, what will happen? The potential, the attraction towards this negative charge will be decreases. Similar to the Helmholtz theory. Same thing. As the distance increases, to attraction towards the negative particles will be decreases. This is a similar thing what will happen. This is regarding same thing. Say only difference is you can see one diffusive double layer theory. You can see one diffusion layer in Guy-Chapman theory. This is also called as diffusive double layer theory. Similar, quite similar, but here you can say only diffusive double layer theory. And this was mathematically expressed as Cx is equal to Cx naught exp minus Z E psi by Kt. You know what is the Cx is the concentration of cations. Concentration of cations at a distance x from the surface. Cx naught is concentration of cations in the bulk solution. Z is a valency. E is a electronic charge. Psi is the electronic potential. Yeah, psi is electronic potential. and K is a Boltzmann constant, and T is absolute temperature. So mathematically, our equation, our thing was expressed by this thing only. Mathematically expressed by this equation only. Our the diffuse double layer theory was explained mathematically like this. So coming to the next. So generally, students, what happened because of the attraction of negatively charged surface, cations in the solution phase tend to distribute themselves over the colloidal surface. So that is what will happen now. Due to the negative charge on the clay surface, what will happen? These cations will be attracted. So attract themselves towards the colloidal. So they will arrange themselves towards the colloidal surface. So what will happen? So naturally we will get some electro neutrality will be maintained. And also this the tendency of these are diffused is countered by the van der Waals attraction. Van der Waals attraction is nothing but attraction towards the between the particles, students. Do you know van der Waals force of attraction chemistry? Very weak force. That force is very weak when compared to other forces. And the attraction towards the negative charged particles will be electronic neutral. At the same time, attraction between the particles of both positive and everything will be counteracted by the van der Waals force of attraction only. So, students, I think you are getting my point. So, negatively charged. So generally the positive charge will be attracted. But and also again these will be also balanced with the with other particles is also balanced with the van der Waals force of attraction. There will be a very weak force of van der Waals force of attraction between the colloidal particles. So the deficit of anion usually present in the liquid surface. Generally due to this exchange and all this thing, definitely there is a deficit of anion will be present into surface. The total charge of the surface constant will be balanced by the excessive cation. So generally that is whenever we found any anion was deficit in the surface, definitely with the help of counterattack of the cations, excess cations will be reduce that deficiency. This usually happens. So generally, the initial electric potential of the colloidal surface is maximum at the maximum. That is what I always I explain. So near the surface, here it is the clay particle negatively charged. Here the electronic potential is very high because it's very near to the closed surface. But as the distance increases from the colloidal surface or the clay particle, what will happen? It will decrease exponentially with the distance from the following. And this distance of the surface, so how this was calculated? It was calculated by this equation. Psi x is equal to psi naught exp minus kx. K is a constant associated. And for this k also there is another equation we will see. So psi x is nothing but electric potential at a distance. So to calculate what is the calculation will be happening between the colloids. So for that is called electric potential. So psi x is nothing but electric potential at a distance x. Psi naught is nothing but surface potential. This is a psi naught, and this is nothing but psi x. Psi x is nothing but your distance. Electric potential at a distance. Psi naught is nothing but surface potential. K is the constant associated with the concentration and valency of ions, dielectric constant and temperature. So K is nothing but it's a constant which is completely dependent upon the valency of ions, concentration, dielectric constant, temperature, etc. And now we will see what at room temperature, what is the constant of the K? As I said, this is a K is a constant. What is that constant? At room temperature, the constant is nothing but 3 into 10 to the power of 7 Z plus or minus root C. So Z is nothing but valency of your ion, and C is the concentration of the bulk solution in the moles per liter. Same thing. So this is explained. This is the equations. Please remember these equations will play a major role in our maybe there is a chance of asking questions. So the Boy-Chapman diffuse double layer theory is equally valid for the both positively charged colloidal surface also. Generally, it is used for the for some positive charged cations also. For positive charged cations, excessive ions will be present in the quite opposite, students. So excessive ions will be present in the liquid interference, and deficit cations will be expected to occur on the surface. Quite difference. During the when there is a positive, say for example, the surface was positively charged. Anions, so what will happen? Generally, the anions will be present in the liquid area. Quite opposite to our regular thing. In regularly, what we will see, clay was negatively charged, cations will be present here. But it is a reverse. If it is positively charged, it will be reverse. This is what happening. But both these phenomena can be explained by this our Guy-Chapman diffusive double layer theory. But students, how the electrolytes will be affect the thickness of the double layer theory. Electrolyte. So for example, if I add some more electrolyte, anything, maybe some acid solution or any base or something was added to the soil, what will happen? The concentration of the cations will be increases. What will happen? Then automatically what will happen? The the double layer will be suppressed. So at high concentration of electrolytes will result in the suppression of the double layer. Generally, what will happen? There is one Cheshire indicated the typical soil system. The thickness of the double layer should be around 1 to 10 nanometers. But when I added the high concentration electrolyte, what will happen? Thus, there is a suppression of double layer theory will be there. By increasing the electronic concentration, the amount of generally the amount of cations will be increases. What will happen gradually? The gradient between the gradient between the surface and liquid will be decreases. What will automatically the thickness of the double layer will be it will be reduced. So the tendency of cations diffuse away from the surface collides decreases, bringing towards the decrease in thickness of the double layer. I think you are following me. What will happen means students, say for example, if you add more electrolyte to the soil, what will happen? The cations will be increases. What will happen then? The diffuse, then the or most of the cations will come very close and fix towards the clay particles, and rest all so the double layer will be completely decreases. The double layer will be decreased. The thickness of the double layer completely decreases. So as the concentration of cations was increases, there will be separation of the double layer will be taken place. This is the major effect of the electrolyte. The thickness of the thickness of the DDL layer. DDL layer means diffuse double layer will be decreases. Okay, students, I hope you're getting my point. If you have any doubts, you can ask. So, what is the valency, sir? So, students, before I'm going to ask this question, I want to ask you few one important question. I hope you will answer for me. Okay, wait. The thickness of the double layer is also affected by the balance of the cations also. Generally, what will happen? The monovalent cations exchange position yields thicker diffuse double layer theory than divalent, trivalent. So like this, is that trivalent, than divalent and trivalent. Because in di and trivalent, what will happen? The diffuse double layer will be decreases. So the phenomena tend to be like this one. So monovalent will have a high thickness, divalent will has a less thickness, trivalent will have more less thickness. That is why what we see, we usually see that sodium and potassium are frequently reported to be responsible of the relative thickness of the double layer than compared with calcium and magnesium layers found by the aluminum are compared to thinnest. Aluminum will be more thin. That is why we can experience that feeling of diffusion, that repropagation due to that heavy thickness of that layer. What will happen? The particles will be diffused very randomly. The sodium content was very high in the soil. So that's why the valency also plays a major role in our diffuse double layer theory. So for overall students, we have to remember only one thing: monovalent will give more thick double diffuse double layer when compared with divalent and trivalent. The trivalent will give very thin. If it is aluminum is present, then it will be very thin. But if you see the divalent will be somewhat better when compared to trivalent. But monovalent will plays a major role in our diffuse double layer theory. This is what you have to remember. So you only remember that monovalent will give a very thick diffuse double layer theory then compared with trivalent and trivalent. So this is what usually. So this is what usually those concepts, the aliphatic concept, and all these things was missed by the Guy Chapman. Actually, there is some problems, some limitations of the Guy Chapman theory. Also, there is some problem is there. Actually, this was completely developed independently by the Guy and Chapman for the application on flat surfaces. They actually these people are not combined. They not work with the work in the same labs. They independently developed this one. What will happen is actually they developed with a flat surface. But later on, what will happen? Some scientists was also settled, but also we can equally apply this concept to the round and spherical surface also by Werner and Overbrick as explained. I said that no, we can explain for spherical surface also. So generally, the negative actually what will happen? The negative charge will consider evenly distributed over the surface, but in clays it is not possible. And also because the counterions are assumed to be point charges and therefore occupying no space, and there may be excessive high concentration at the liquid interference. And also students, what will happen? You just imagine those are the only point charges. So the point charges, and you imagine that there will be excessive high concentration will be there. And also didn't talk anything about the valency and all those things. So there are a lot of limitations will be there. And also you think that I believe that Goy Chapman model taken into account of simply taken electrostatic forces by which cations with similar valency are observed similarly. He indicated that cation exchange reactions of lithium, potassium, and calcium, magnesium, for example, held attracted by different forces of clay surfaces. So generally, the lithium is completely force of attraction is different, potassium is different, calcium is different, barium is quite different. Okay, students. So he missed many things. He didn't give any much proper explanation because there is no. He didn't consider about the valency and all those things, and also he thinks that there's a point charges are present on the clay surface. All those things. So it is not possible. So to overcome This sort of small problems, what will happen? We have seen the one person that came called Stern double layer theory. Stern double layer theory is nothing but it's completely combination of above both Helmholtz and double layer theory. Quite similar, students. This theory was quite similar, but only difference is that the second layer, first layer was completely fixed, it was negatively charged. But the second layer of diffuse double layer theory was divided into two layers, what is called the near the sublayer. One is sublayer, and another second one is called the first one is called sublayer near the colloidal surface. Second one is called the diffusive double layer. I will show the yeah. This is one. This is called the Stern layer. This is called the Stern. This is a this is the first layer called Stern layer, and this diffuse double layer also has been divided into two. So this is nothing but students. Stern made corrections in he made corrections in double layer theory by taking into consideration of ionic dimensions. Here took the ionic dimensions. The influence of the ionic dimension greater near the colloidal surface. In colloidal surface, the influence of the ionic dimension is important. In Stern theory, the first layer is similar to that of previous theory. See, in Stern theory, first layer, this first layer was quite similar to that of very previous theories. So Helmholtz or diffuse double layer theory. But only difference is that the second layer is divided into two. One is called sublayer near the colloidal surface, and another one is called diffuse layer, colloidal surface, diffuse layer. The first layer is tightly packed with cations, is called the Stern layer. So this is negatively charged. This layer is completely similar to the previous theories, all negative charge. And this first layer is called Stern layer, students. This Stern layer is completely tightly fixed, so tightly packed with cations. Here we can see completely tightly fixed cations will be there. And the potential distribution appear to be combination of Helmholtz and Guy-Chapman diffusive double layer. What is the how the potential will difference will be there? Quite similar to our Guy-Chapman theory. What Guy and Chapman said that as the distance increases, the potential towards the attraction will be decreased. Same thing was repeated in this channel layer also. So the decreasing in potential and also the decreasing in potential. What the stem said, the decreasing in potential is also divided into two parts. In Stern layer, the potential decreases with the distance from the surface according to the Helmholtz theory. Similar, students, as the distance increases, the potential also will be decreases. Helmholtz theory. From here, as the distance from here to here, the potential decreases. After, when it comes to the diffusion layer, the decreasing in potential will follow the Guy-Chapman theory. From here it is follows the what Helmholtz system. But here you can see Guy-Chapman diffusion layer theory. Guy-Chapman, what it is completely a diffusion layer. Complete here the potential difference is completely explained by the diffusion layer theory of Guy and Chapman. So this is regarding the Stern layer theory. Stern layer theory is nothing but combination of above both Helmholtz and so-called diffuse double layer theory. But only difference is that he divided the second layer into two, inner and outer. Inner is nothing but Stern layer. Stern layer is a fixed layer. All the cations will completely fixed very tightly. But in diffusion layer, here you can see all the diffusion particles will be. Here you can see follows the Guy-Chapman system will be followed. But here you can see Helmholtz and Helmholtz systems will be followed here. This is what, student. There is no much difference is there. The only difference, the division has taken place here. And he also given emphasis on the valency of our cations. So same thing which I explained here, I given in a theoretical form. It just this for a reading purpose. Coming to next is called triple layer theory. Triple layer theory, as I said, this is for the oxides, SQ oxides. So generally, all the theories what we have read in our previous slides will completely explain the how the charge, how the diffusion, how the layers will be taken part in silica oxides. But here this triple layer is completely explained about the SQ oxides. So this is the example, student, regarding the SQ oxides. Uh, So, however, surface properties of SQ oxides and other type of clay exhibiting oxyhydroxyl surfaces. That's what, students, oxides will be present on the SQ oxides are somewhat which different with those of silicate clay minerals. This is quite different. So this type of potential determining ions, that's OH minus ions, that is potentially different in minus ions, you can't expect in silica oxides, but you can expect in our SQ oxides. SQ oxides. However, the surface properties of SQ oxides and other type of clay exhibiting oxyhydroxyl surfaces are somewhat different from those of silicate clays. Okay, students, this SQ oxide charge is somewhat quite different from that of permanent charge, which is developed by osmotic substitution. The permanent charge in the oxide clays complemented or shielded with the shielded on the clay surface by the charge attributed to the adsorption of the potential determining ions which are present H plus and OH minus ions. So whatever the permanent charge was developed on the sesquioxide clay minerals was completely covered or shielded by this OH and potentially determining ions. Potential determining ions are nothing but your OH minus and H plus ions. So these are completely covered with this OH minus H plus in sesquioxides. The surface was completely shielded by this OH and H plus ions. So what will happen because of the presence of this potentially determining ions? What will happen? Adsorption and traditional counter ions is localized in the zone further outward and mineral surface. So this model is called triple A. So overall, students, to your remembrance, this is a clay particle. This is a clay particle. Already there is some charges there. At the same time, these clay particles are counteracted by the or shielded by the potentially determining ions like OH minus ions, H plus ions. And also again, so there is one additional layer was formed here. At the same time, in diffusion layer, you can see additionally there are two layers. That's called inner Helmholtz and outer Helmholtz. So the inner Helmholtz, what is this inner Helmholtz and outer Helmholtz? It's nothing but in fact the localized liquid surface. It is perhaps called the effective first layer. This is called the effective first layer in the double layer. The next layer is called the liquid surface. It's called effective for this potentially determined layer is called effective first layer is divided into this effective this potentially determining layer, and this effective layer is completely divided into inner and outer Helmholtz layer. The inner Helmholtz layer is the zone for the specific adsorption of the traditional counterions, whereas outer Helmholtz, so inner Helmholtz is nothing but the traditional, it's absorption for traditional counterions. The outer Helmholtz layer represents a zone which gradually changes into diffusive layer. So here we can see some traditional attraction towards this potential determining ions will be there, but here in diffusion layer we can see some it can be replaced. So there you can see some diffusion layer. So this, it will be near to the diffusion layer. All the clay particles, all the positively charged particles will diffuse towards diffusion layer. The aluminum sometimes there is aluminum. This aluminum may sometimes replace with iron also. There is a chance of iron. So like this, you can see in sesquio oxides you can see three different layers. The only difference, students, this the negative charge is completely shielded by the potentially determining ions in the sesquio oxides. Those potentially different ions is nothing but OH minus ions. So we get one additional layer here. And also in next layer, preceding layer is completely divided into two, inner Helmholtz and outer Helmholtz. In inner Helmholtz, you can see traditionally attracting of a positive charge. But in outer Helmholtz, we can see some diffusion. This towards the diffusion layer. So you can see some diffusion positive cations will be taken place here in inner Helmholtz. So this is regarding the potential layer. This is regarding the triple layer. Triple layer is a quite similar, students. All are quite easy. As the distance increases, the potential towards the attraction of the negative charge is completely decreases. Quite similar. Everything is this line was similar, constant for all the models. Every model is saying that as the distance increases, the attraction towards the clay particles also will be decreases. So this is regarding the potential of the regarding the triple layer theory. I think you should. It's very simple. For your remembrance, this theory is usually applicable for our sesquio oxides. Same thing, students, which I explained. The same thing was present here in the theoretical model. This is for your reading purpose. So coming to the zeta potential, very important thing, students. Zeta potential is nothing but the electric potential developed at the solid and liquid interference is called the zeta potential. The electric potential developed at the solid liquid interference is called the zeta potential. The zeta of the angle is represented by the chi. This symbol is called chi. This symbol here is there now. This is called symbol. This is called the chi. This is called chi, and this is called the psi. Psi. This is called the psi. I hope you should remember all these Greek words. Okay. So like this, the seat of zeta potential is the shearing plane or slipping plane. So this layer is called nearby the wherever the zeta potential is present. That is called the slipping plane, or this is called slipping plane, or you can say shearing plane between the bulk liquid and envelope of water movement in the particle. So this is called the shearing plane where the zeta potential is very high. And since the position of so generally, students, this slipping plane is we don't know because we don't. This is some unknown layer, so we are just imagining. So this may be present here, sometimes here also it will be present. So so this is unknown zeta potential, and also it's a chemical potential on the colloids. Generally, this zeta potential is nothing but So remember, it is nothing but electrical potential developed. It is a potential between the. Well, students, so this is regarding the zeta potential. It is zeta potential. Usually, that potential, that particular area is called slipping area. Slipping area. So this is, we don't know. We don't know where it is present. What happened? Yeah, viscous is, so this is potential. So generally, so how this zeta potential will be affected by the electrolyte? So students, when we add an electrolyte to the particular solution, what will happen to the liquid double layer? It will decrease or increase? Will increase or decrease? Students, please. The zeta potential. So the thickness of the double layer affected the magnitude of the zeta potential, students. Generally, increasing in the electrolytic concentration in the solution usually result in the decreasing in the thickness of the double layer, which we have already discussed in our previous slides. They were decreasing in the double layer theory. Compression of the double layer will also occur by the increase in the valency of the cation, valency of the ions also, as I said. So monovalent will give more thickness, divalent less, trivalent is very less, which usually we have discussed. Okay. The potential, the zeta potential, the psi potential may therefore be expected to decrease with increasing in the electronic concentration. So as the potential will be decreases, students, as the thickness of the decreases, as the thickness of the as the electrolyte concentration was increases in the solution, what will happen? The zeta potential also will be decreases. What will happen at certain position? What will happen at the critical position? The point at which the potential will become zero. So the zeta potential will become zero. That is called isoelectric point. So when the zeta potential is zero, it is called the isoelectric point. So when we added electrolyte, what will happen? The thickness of the double layer will be decreases, and that is called the isoelectric point. I hope you are getting my line. Okay, students. Next we see next one. So this isoelectric point, usually this also can be calculated. The potential is a unique property of the colloid, but it depends upon the surface potential also, students. And this is mathematically expressed with this formula. V is equal to D. This is nothing but the surface for the zeta potential E by 4 pi rho. V is nothing but electrokinetic valency. D is dielectric constant. E is amplified EMF, electromotive force, and this rho is this eta is called, what is this? I think rho or eta. 1 minute, students. I will check it. Yeah, eta. This is eta. This is called eta. It is nothing but viscosity of the fluid. This is the viscosity of the fluid. Is so this completely this isoelectric point double layer is completely calculated with this V is equal to D zeta potential E by 4 pi eta. Please note down these formulas. These formulas are very important, and these derivations also is there regarding for this with these equations. But for examination point of view, I'm not interested to say all those things. So with these students, I have explained very basic fundamental. I have explained, but my request. So please, once you learn this, once you learn, will learn in your textbooks, you'll get better idea. And if I have any doubts, please, no need. You just put me WhatsApp, or you can telephone. You can call me also. You can call me at any time except in working hours, like 10 or 11, 12. Don't call in evening times. You can call me at 8 to 9. I'm always free. You can call anytime, and please try to discuss the subject. Exams are coming very fast, so please be prepared thoroughly and be confident. Everyone, be serious. I will take classes regularly, and I will try to take classes regularly to arrange my timetable. Thank you very much, students, for your the belief patience came at this morning.